The goodness of fit, I want to discuss that quickly.
The data have been randomly selected. 2, the sample data consists of frequency counts for each of the different categories. 3, for each category, the expected frequency is at least 5. Recall binomial NP greater than or equal to 5 and NQ greater than or equal to 5. The expected frequency for a category is the frequency that it would occur if the data actually have the distribution that is being claimed. There is no requirement that the observed frequency for each category must be at least 5. 4, there is a single question or outcome of an experiment from a single population. 5, the distribution is either a uniform distribution or it fits a given distribution.
So those are the requirements, and the bottom line is the goodness of fitness deals with proportions. But if you recall, when we dealt with the binomial distributions, there were 2 outcomes. What if we have more outcomes now? Okay, a simple example, when you roll a die, there are 6 outcomes. So the probability in each case is 1/6, right? If you have a fair die. What if it's not? What if it's loaded? Fine, whatever that the numbers are. It's just that whatever the claim is, does it work or not? That is the idea of goodness of fit. So H0 is the frequency counts. The frequency counts agree with the claim distribution, and H1, they do not. And the test statistic basically measures the disagreement between the 2. So are the differences between the actual observed frequencies, which we call them O, and the theoretical, that is the expected frequency, is that those differences, are they significant or not? That's what the test of hypothesis of goodness of fit. Now, in the case of a goodness of fit, there are a couple of things. When we have equal frequency, E can be calculated as N/K, or E equals N times P proportion, if you will. The critical value is using the chi-square table, and it is always set up such that it is a right tail test, and that is equal to the summation of O minus E quantity squared over 2. And I'm explaining here as to why it's a right tail test. If the sum of this weighted square deviation is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution. Only when the sum is large is a reason to question the distribution. Therefore, the chi-square goodness of fit test is always a right tail test. All right, then we go through the p-value, and then the formula. If you look at the test statistic, chi-squared is O minus E squared over E is the summation of that. Degrees of freedom is K minus 1. And it is explained what does O, E, K, N, and P represent. Also, how you calculate that using